between the test points and
questions?
Tell you when to stop. Possibly involve easily another type of uncertainty. That means if the training set is not clearly classified in some sense that some examples are not typical and take a lower influence on the result. And this is another thing which is desirable and could be possibly included in this approach as well.
No, I'm interested in the influence of the aggregation. Yeah, because my opinion it is better not only that this additional explanation is helpful, but explain why it is helpful. Yeah? For example, your approach reminds me another approach in classification based on so-called kernel trick. And it seems to me that what you are proposing very similar. However, your explanation, yeah, I do not see the similarity actually, yeah, because kernel trick is nicely semantically explained, yeah. So this is a kind of increasing dimensionality of your data points, yeah. So including parameters that really help make classification, yeah. So my question or proposal just first of all compare with this kernel method, and second try to explain in which position this aggregation really helps and why it is helpful. Some deterministic approach.
Thank you, Valerie. To move to the second talk, which is going to be online. It's discovering fuzzy and statistical patterns in data, the Nuggets R package, by Burda Michal. Yes, and it's going to be online.
Yes, thank you for introduction. Can you hear me? Hello? Can you hear me?
Yes, hello.
Great. So I will show my presentation. Okay, so good morning, everyone. My name is Michal Burda. I would like to present you my previous work on some software for statistics and data mining. I'm glad to have the opportunity here to present this work to let the broader audience to know that something like the package that I will be speaking about even exists. So the name of the package is Nuggets. So what was the motivation for my work? I want to analyze the data, mainly to discover hidden regularities in the form of patterns and also to utilize the fuzzy logic. I want also to enable me and others to discover or research on new patterns or new statistical evaluation, visualization, or interactive exploration. So the goal of the work was to provide an extensible framework for data pattern search. So what is Nuggets? Nuggets is an R package, so for the R statistics software, and it is a library for discovering patterns based on frequent logical conditions, or it is also known as frequent item sets when the data are crisp. So here we can work not only with crisp data, but also with fuzzy predicates. The search is driven by support. That means the frequency of the condition, and the package simply searches for all frequent conditions and where you can evaluate your metrics, your measures on them. It works on Windows, Linux, and Macintosh operating systems, so there is no problem to work on just everywhere. The central abstraction is a condition. Condition here is an elementary conjunction of predicates. So in crisp mode, we have a predicate that has truth value only true or false, 0 or 1, and the conjunction is simply the Boolean conjunction. In fuzzy mode, we have truth values from the degree, in the degree is the degree from 0 to 1, and conjunction is any chosen t-norm. The package supports standard t-norms such as Gödel, minimum, Gauguin product, or Lukasiewicz t-norm. The package simply generates candidates of conditions, obtains their support, which is the mean value of, or average value of truth values of a condition, and if that condition is frequent, so the support is above some specified threshold, you can further process it to obtain some pattern as of your will. So the core principle here is to enumerate frequent conditions and then decide what interesting means. So it's up to you to say whether the pattern is interesting or not based on some test or some computation. There are also some patterns that are currently supported. The most well-known are association rules. So these are rules in the form of implication. For instance, if age is high and cholesterol is high, then the heart disease is very probable. So if you have data set with patients, their age, their cholesterol, their other indicators, then you can process that data set and obtain rules in the form of implication. You can measure the interestingness in more than 53 measures, so that they are available in the package already. Another type of rules are conditional contrasts. The example is that a rule that mean income on ice cream is much higher than on tea if the weather is hot. So this type of rules captures differences in means or proportions in some subsets in data, and the subset is determined by the condition. So you simply evaluate a multiple amount of hypothesis tests and search through some search space for such high differences in mean value of some numeric variables. The third type, already available in the package, are conditional correlations. It's similar to the previous type because you search for a condition under which two numeric variables highly correlate. So, for instance, you can find that sales on ice cream correlate highly sales on cold beverages, again if the weather is hot, and so on. So this is already available there. Here is a minimal example how you can obtain some rules. In the first line, you install the package, so it's one line installer from the R environment. On the second line, you load the package nuggets into your workspace. After that, you have to pre-process the data to create predicates from numeric variables. There is a function partition which allows to apply different methods of falsification of data for different types of fuzzy sets and so on. And after that, you simply search for association rules by running a single function associations. You put there your data, your constraints of what the rules should be, how they should look like, some constraints such as maximum length of the condition, minimal support, and so on. And after a while, you obtain your results, which you can explore interactively by the function that is called explore. This package is also extendable, so you can give the engine your custom callback function, and this callback function can be executed every time the engine finds effects and conditions. So instead of predefined rules, you can search for your own rule types. You can experiment with new definitions of patterns. So this package allows for fast prototyping of new pattern types. You can experiment a lot. Here is again some simple example for those of you that are familiar with R language. You simply define your own function. You expect some inputs to the function, and you can provide custom computations inside. After that, you run the general searching method. You provide your data, your thresholds, and also the function you created, and the engine searches for frequent conditions and executes your function for each condition the engine finds, and then it collects all the results you provide to it. So that way you can explore various combinations of conditions and obtain your own patterns. So the design intent here was to separate mining or searching the engine from meaning what will be computed. That's in your callback. The package also allows interactive exploration. The idea is that the pattern discovery is inherently exploratory task. So analysts need filtering, visualization, manipulation with the results to get the knowledge from the obtained rules. So in the package, you can find the function explore, which launches an interactive application for pattern exploration. And this application allows for filtering, sorting, and various visualizations. I have some screenshots here. You can see the window of that interactive tool. You will see there the table of rules that were obtained in the data. You can filter by all different columns that are there, the measures of interest. You can look at the details for each pattern and explore what's inside, how it is constructed. You can do some clusterings of patterns. and so on. So the tool is growing all every day, so and new features are added here. So I hope it will be interesting. So to conclude, the Nuggets is a framework for fuzzy and statistical pattern discovery. It benefits greatly from the R ecosystem because R software is very good at data loading, processing, reporting, visualizations. So this Nuggets package adds an additional functionality that is that targets at searching for patterns. The package also already contains built-in searching tools for association rules, contrasts, conditional correlations. It is extensible via user-defined callback. It contains interactive Explorer app application and works on hopefully almost all devices like Windows, Linux, or Macintosh operating systems. So if you want, you can look at these pages where is the documentation. I hope the documentation is quite large. So every aspect is documented here, and you can download and install and use freely. So yeah, so that's all. Thank you. Have you any questions?
Oh, we have time for questions. Thank you very much. Guri, about improved
tracking all getting the mean or
Take the simulation.
Inside the aggregation, similarly between classes, like we have two classes.
Inside, you mean? Inside one class. Between class. I mean, here's the fuzzy. I have some track about iterated correlation under
start like why do we do associates that are widely and machine learning practical question that we're going stable is the iteration at a certain step. So this could be done like by time series simulation or modeling, but today we're gonna do it in a different way. Okay. So again, this is the initialization of how we iterated the correlation. Again, we started like with a random matrix initialized from a uniform distribution, and then we iterate, and we have like the threshold or like the tolerance here, 10 to the power minus 12, where the iteration will stop. And here we have taken like the maximum element-wise difference. But even if we do it by the Frobenius difference, it's gonna be like the same. But this is like local, and the Frobenius is like global. So the step size here is delta K, which is like the Frobenius difference between the two iterates. And we measure also the contraction ratio at each step. And also we build the envelopes for rho given delta. All right, rho is the contraction ratio and delta is the difference of the step size, or the Frobenius difference. The empirical laws that we have like got throughout all this experiment, like we have done around 1,000 trials per each matrix size, and these sizes were like variable, like from small to medium to large, but the maximum matrix size was like around 2,000 by 2,000. Here we have like a first step contraction, which is like a universal for all the matrices, all the trials. The second law is the quasi-monotone decay, where this step size decreases with bounded overshoots, and then the updates will stabilize later. And we have like the universal contraction law, which is the main topic of today, which is the V shape. And it collapses into a V shape, this relation, like we plotted the points, delta K and rho K, and then they collapse into this V-shaped curve that we're gonna see in the figure. The fourth empirical law was that the iteration counts to reach convergence is like bounded, and technically we have like 22 steps regardless. This was like the maximum number of steps to reach convergence for all the matrix sizes that we have experimented. So this is the universal V shape. Here we plotted like, you can see like within each color, the colors here, they represent each matrix size. For example, I think the red, it represents the matrix 2000 by 2000. And all of them, they behave like similarly. We have like this V shape. And then we can see that the strong contraction for large delta K, and we have like near isometry with small overshoots where like the contraction goes more than 1, and this happens as delta K goes to 0, like near convergence, we have the overshoots. So here is the main result, and then from this figure we want like to check what happens technically at each step size, and when we're gonna have like the overshoots, and are they controllable, yes or no? So in order to do that, we go from a law to a prediction problem. So here, if the probability of this contraction ratio is less than PB of delta K, is approximately P, then we can like check what we're gonna do. And here BP of delta K can be like any layer that we're gonna present later. And here we can like monitor stability, flag the unusual updates, and also guide the stopping rules. Like it has so many uses. So the layer one, which is like a simple predictive statistical layer. Here G of delta is like the mean, and then sigma of delta is like the dispersion, and mainly that's it. It's like a simple statistical layer. And with confidence P, we can say that the contraction ratio stays below this curve, yes or no. All right, so if it's like above this curve, we're gonna have like something that is not going normally, or an overshoot. Tail number 2, we keep like, this is like, we keep like the median the same, but we inflate the dispersion. All right, we inflate it like with e to the power tau squared over 2, and this like is being used like also in a paper by Taleb and Cirello. Like they have used this to inflate the error. It's like the error on error, so it's allows like maximum safety against uncertainty. All right, so this will be like our second layer, and the third layer we build the third layer on the second layer, not on the initial one, not on the initial data. And this is like the fuzzy one, which allows like tolerance margin. And we can like use that even more. But technically here, if alpha is 1, so we're gonna have like the same as layer 2. Yeah, so layer 3 will be like equal to layer 2. And if we're gonna have like smaller alpha, then the margin will be increasing up to 1 plus lambda. All right. Now the ordering technically is the first one, the first layer, which is like the simplest statistical one. Then we're gonna have the inflated error one, which is QTC. Then we're gonna have like U alpha one, which is the fuzzy one. Again, here we have separation because like the learned geometry is like from the initial data, it's learned from the data where we have like G of delta and sigma of delta. And we have the user controlled parameters, which is P, which is the confidence level, tau, the tail conservateness, and alpha and lambda, which is the tolerance margin. Now, in order to check like if we what have done like is literally applicable, we do like an out of sample validation. And here we evaluate based on, we fit G of delta and sigma of delta based on 70% of the collected data. And then we use the 30% as unseen trials. And we have here, if you can see, sorry. What happened? Where we are. So yeah, this dashed line is like the calibration line, all right? The red line, it represents the first layer, layer number 1, which is the simple statistical layer. If you can see, the green one represents the one with the inflated uncertainty, and it's technically above the dashed line. Yeah. So if we miss with the naive one, because like here for P around 0.84, let's say, we have like the red line under the dashed line, which this means that we are not doing well, something is wrong. And we can see like the green line is above, which is more conservative. The blue as well, which is fuzzy when alpha is set to 0.9, and also when alpha is 0.5. So yeah, that's it. So how are we gonna use this? Technically, the most important are QTC of delta K and U alpha. And we have 2-level decision tolerance here. For example, if rho K is less than QTC of delta K, this is like expected contraction behavior. It's all right. If it is between QTC and U alpha, this is like alarming, yeah, or warning, not alarming. We can say like at this point, rho is getting like more than 1, but it's not very dangerous, or it depends like on what you want or how you're modeling it. But the alarm is technically if it's more than U alpha, and also it depends on the value set for alpha in this case. So these are the parameters, meaning like P sets the confidence, tau at state safety, and alpha lambda controls the balance tolerance above the QTC. This is like the technical validation. I don't know if we have more time, but we can skip it. The summary. So for the iterated Pearson correlation, it exhibits definitely stable empirical laws, including a size-independent V-shaped contraction pattern. And we learned the baseline geometry from the data, definitely the median curve and the dispersion profile. These are data inherited. We did not invent them. Okay, and then from the G and the sigma, we built the predictive upper envelopes with increasing safety. And then we provide the practical rule to monitor, stop, and flag abnormal updates. And we can use this in real life applications that could be in machine learning or any other. Yeah, and these are the references. And I'm ready for your questions. And thank you.
Thank you. Questions, please?
Mhm.
Question. I call this upper bound fuzzy because it looks like after you use it as a crisp, because you have like a glass or up, so the same crisp conditions after.
What do you mean, the same conditions?
I mean, when you calculate the fuzzy upper bound,
Yeah.
after you use it as a crisp bound, so
Yeah, as a tolerance, like if,
as a tolerance.
yeah, but like, you can like, it depends on the parameters you set. It depends on how you want to control your decision or how you want it to be.
I understand.
Because it is fuzzy, you know? Yeah.
Like philosophical why it's fuzzy. I mean, because it's from the 0 to 1 or.
Yeah, well, yeah, and then you can like control it based on these values, like they alternate, like alpha and lambda, and so on. You're welcome.
Okay, we finished this section and we are quite fast for lunch. So enjoy the lunch. Thank you.
Thank you.